As the relative size of the cation gets smaller, eventually it is no longer possible to maintain the cation-anion contacts and simultaneously keep the anions from touching each other. When this occurs, the coordination number drops from 8 to 6 and the sodium chloride structure becomes more favorable. As the cation size decreases further, eventually the coordination number must be reduced again, this time from 6 to 4, and the zinc blende structure becomes favored. Remember that in ionic crystals, ions of opposite charge touch each other, but ions of the same charge should not touch. The relative number of cations and anions also helps determine the most stable structure type. All the structures in figure 12.26 have equal numbers of cations and anions. These structure types, cesium chloride, sodium chloride, zinc blende, can be anions. These structure types, cesium chloride, sodium chloride, zinc blende, can be realized only for ionic compounds in which the number of cations and anions is equal. When this is not the case, other crystal structures must result. As an example, consider NaF, MgF2, and SCF3. Sodium fluoride has the sodium chloride structure with the coordination number of 6 for both cation and anion, as you might expect since NaF and NaCl are quite similar. Magnesium fluoride, however, has 2 anions for every cation, resulting in a tetragonal crystal structure called the rutile structure. The cation coordination number is still 6, but the fluoride coordination number is now only 3. In the scandium fluoride structure, there are 3 anions for every cation. The cation coordination number is still 6. But the fluoride coordination number has dropped to 2. As the cation-anion ratio goes down, there are fewer cations to surround each anion. And so the anion coordination number must decrease. The empirical formula of an ionic compound can be described quantitatively by the relationship number of cations per formula unit divided by number of anions per formula unit equals anion coordination number divided by cation coordination number. Page 494, molecular solids, where I stopped after I got assaulted, bullied, harassed, and attacked. On my second day of pediatric neurology school, wherever I am, wherever I am in outer space, in silence. The Halide Perovskites, exemplified by methyl ammonium, lead iodide, CH3NH3PBl3, whose structure is shown here and on the front cover, have emerged in recent years as alternatives to conventional semiconductors such as those that get sold in Taiwan and bought at the University of Washington in silence. Like silicon, gallium arsenide, and cadmium selenide, these materials show tremendous potential for use in devices such as light-emitting diodes and radiation detectors, important for when the Russians end up destroying Earth for what everyone calls no applications, has generated more excitement than their performance in solar cells to keep them in their bunkers with fake food and fake oxygen when their duality in mathematics and silence ends in silence. Scientists have been able to prepare Halide Perovskite based solar cells that convert sunlight to electricity with 20% efficiency. The efficiency of the combat that happened in Iraq and Afghanistan for a longer amount of time, for 20 years, with less death in a few months from the bullies who assault me in silence. While the high efficiencies are impressive, the truly revolutionary breakthrough is that Halide Perovskite solar cells can be made from solution using inexpensive, readily available laboratory equipment. Whereas fabrication of solar cells from conventional semiconductors sold in Taiwan and China now, one China in silence, one Russia and one China in silence. Sophisticated facilities. Chemists are actively searching lead-free perovskite materials that are less prone to degradation upon exposure to moist air. In other words, when the bully comes for you all, be prepared for that 200 pounds he carries on the street he says he owns in silence. In silence.